Picture this. It's 1948. The Cold War is just beginning to freeze the world in fear. In a classified hangar somewhere in Southern California, Douglas aircraft engineers are hunched over blueprints for what would have been the most terrifying machine ever to take to the skies. A bomber so massive it would dwarf today's largest passenger jets. A flying fortress designed around one singular apocalyptic purpose: to carry a 25-megaton thermonuclear bomb to any target on Earth without refueling. They called it the Douglas 1211-J, and if it had been built, it might have changed the course of human history forever. Welcome back to Never Built, where we explore the most ambitious technological failures in human history. I'm your host, Ethan Caldwell, and today we're diving deep into one of the most audacious aircraft designs ever conceived. A machine so large, so complex, and so ahead of its time that it reads more like science fiction than historical fact. Before we begin this incredible journey into aviation's lost future, make sure to hit that subscribe button and let me know in the comments. Do you think the world would be safer or more dangerous if the Douglas 1211-J had actually taken flight? Your thoughts might surprise you by the end of this story. The Douglas 1211-J wasn't just a bomber. It was a flying aircraft carrier, capable of launching and recovering its own fighter escorts mid-flight. It was an engineering marvel that would have required rebuilding America's entire airport infrastructure. And it was the last desperate attempt by the United States to create a propeller-driven aircraft capable of single-handedly destroying an entire nation. But why was it never built? And what does its failure tell us about the thin line between visionary engineering and catastrophic overreach? Let's find out. To understand the Douglas 1211-J, we need to step back into the immediate aftermath of World War II. The year is 1946. The atomic bombs dropped on Hiroshima and Nagasaki have fundamentally changed warfare forever, but nuclear weapons are still primitive, massive things. The Fat Man bomb that destroyed Nagasaki weighed over 10,000 pounds and was nearly 11 feet long. These weren't weapons you could strap to just any aircraft. The United States Air Force was facing a strategic nightmare. The Soviet Union was rapidly developing its own nuclear capabilities, and American military planners knew that any future conflict would likely be decided by who could deliver nuclear weapons most effectively. The problem was range. Existing bombers like the B-29 Superfortress had proven themselves in the Pacific theater, but they couldn't reach targets deep in the Soviet Union and return to base without multiple aerial refuelings. Enter Douglas Aircraft Company, the same firm that had produced the legendary DC-3 passenger aircraft and the SBD Dauntless dive bomber. In late 1946, Douglas received a classified contract from the Air Force to study the feasibility of an intercontinental strategic bomber. The specifications were staggering. The aircraft needed to carry a nuclear payload of at least 20,000 pounds over a distance of 5,000 nautical miles without refueling. The lead engineer on the project was Arthur Raymond, a brilliant aeronautical designer who had cut his teeth on some of Douglas's most successful aircraft. Raymond looked at the requirements and realized immediately that conventional thinking wouldn't work. You couldn't just scale up existing bomber designs. This would require a completely revolutionary approach to aircraft engineering. Raymond's team began with the most basic question: how big would this thing need to be? Their calculations were mind-boggling. To carry the required payload over the required distance, the aircraft would need a wingspan of over 230 feet. For comparison, that's wider than a football field is long. The fuselage would stretch nearly 200 feet from nose to tail, making it longer than the Wright brothers' first flight. But size was just the beginning of the challenges. The aircraft would need to fly at altitudes above 40,000 feet to avoid Soviet interceptors. Yet it would also need to be stable enough for precision bombing runs. It would need to operate in all weather conditions, from Arctic cold to tropical heat. And perhaps most challenging of all, It would need to be maintainable by existing Air Force ground crews using existing tools and techniques. Raymond's solution was elegant in its audacity. Instead of trying to build one massive aircraft, he proposed building what was essentially a flying aircraft carrier. The Douglas 1211-J would carry its own escort fighters, launching them when approaching enemy territory and recovering them for the return journey. This would solve the range problem for fighter escorts while providing the bomber with its own defensive capability. The initial design called for 4 massive turboprop engines, each producing over 6,000 horsepower. These weren't the relatively small turboprops we see on regional aircraft today. These were monsters with propellers over 20 feet in diameter. The sound of all 4 engines at full power would have been audible from over 50 miles away. What do you think drove these engineers to dream so big? Was it pure ambition, or were they dancing with destiny in the shadow of nuclear war? The answer might surprise you as we dig deeper into this incredible story. By early 1947, Douglas had produced preliminary designs that left even seasoned Air Force generals speechless. The 1211-J would be the largest aircraft ever built, dwarfing even the massive Hughes H-4 Hercules flying boat. But as impressive as the initial designs were, the real engineering challenges were just beginning. Arthur Raymond and his team at Douglas faced engineering challenges that had never been attempted before. The sheer scale of the 1211-J meant that virtually every component had to be designed from scratch. There were no existing engines powerful enough, no landing gear strong enough, no control systems sophisticated enough for an aircraft of this magnitude. Let's start with the engines. The 4 turboprop power plants specified for the 1211-J would each need to produce over 6,000 horsepower continuously for flights lasting up to 18 hours. To put that in perspective, that's more power than most World War II destroyers produced from their entire engine room. Each engine would consume fuel at a rate of over 400 gallons per hour, meaning the aircraft would need to carry nearly 30,000 gallons of fuel just for a one-way mission. The propellers presented their own unique challenges. At 22 feet in diameter, they were larger than the entire wingspan of many fighter aircraft. The tips of these propellers would be moving at nearly the speed of sound, creating shock waves that could potentially tear the aircraft apart. Douglas engineers had to develop entirely new materials and manufacturing techniques to create propeller blades that could withstand these incredible forces. But perhaps the most complex engineering challenge was the aircraft's structure. The 1211-J would have a maximum takeoff weight of over 450,000 pounds. That's heavier than a fully loaded Boeing 747. The wing structure alone would need to support this enormous weight while maintaining the flexibility necessary for flight. Douglas engineers developed a revolutionary wing design using a combination of aluminum and steel with internal bracing that resembled the framework of a skyscraper more than a traditional aircraft wing. The landing gear was another nightmare. Conventional aircraft landing gear simply couldn't support the weight of the 1211-J. Raymond's team designed a complex system of 32 wheels arranged in 8 four-wheel bogies. Even distributed across this many wheels, each wheel would still be supporting over 14,000 pounds during landing. The tires alone would cost more than an entire fighter aircraft. Inside the aircraft, the engineering challenges continued. The crew compartment needed to house 12 people for flights lasting up to 20 hours. This wasn't just a matter of providing seats and basic life support. The crew would need sleeping quarters, a galley for food preparation, and even recreational facilities to maintain morale during these marathon flights. The aircraft essentially needed to function as a flying hotel. The navigation and communication systems were equally complex. Remember, this was 1947. There was no GPS, no satellite communication, no computerized flight management systems. Navigation would rely on celestial observation, radio beacons, and dead reckoning. For a mission to the Soviet Union and back, navigational accuracy would be literally a matter of life and death. A small error in navigation could mean running out of fuel over the Arctic Ocean or accidentally violating neutral airspace and triggering an international incident. Douglas engineers also had to solve the problem of pressurization. At the aircraft's planned cruising altitude of 42,000 feet, the outside air pressure is less than 3 pounds per square inch. The human body cannot survive at that altitude without pressurization. But pressurizing such a massive aircraft presented enormous structural challenges. The pressure differential between inside and outside would create forces trying to tear the fuselage apart like an overinflated balloon. The electrical systems alone were more complex than those found in most buildings of the era. The 1211-J would require over 50 miles of electrical wiring, multiple redundant power systems, and backup systems for the backup systems. A single electrical failure during a 20-hour mission over enemy territory could be catastrophic. But perhaps the most audacious engineering challenge was yet to come: the aircraft's ability to launch and recover its own fighter escorts. This wasn't just a matter of carrying extra aircraft. It required developing an entirely new system for aerial launch and recovery that had never been attempted on this scale. As 1947 progressed, it became clear that the Douglas 1211-J was pushing the boundaries of what was physically possible with the technology of the era. But Raymond and his team pressed on, driven by the knowledge that America's nuclear deterrent might depend on their success. The question was, could they actually make it work? The most revolutionary aspect of the Douglas 1211-J wasn't its size or its range. It was its ability to function as a flying aircraft carrier. This concept, known as a Parasite Fighter System, would allow the massive bomber to launch and recover smaller fighter aircraft during flight. It sounds like something out of a science fiction movie, but Douglas engineers were deadly serious about making it work. The concept wasn't entirely new. During World War II, both the United States and Soviet Union had experimented with Parasite fighters. The U.S. Navy had successfully operated small fighter aircraft from the rigid airships USS Akron and USS Macon in the 1930s. But those experiments involved relatively small aircraft operating from relatively slow platforms. The 1211-J would be attempting something far more ambitious. Raymond's design called for the bomber to carry 4 McDonnell XF-85 Goblin fighters. These were tiny, single-seat aircraft with a wingspan of just 21 feet. They were essentially flying engines with guns attached. The Goblins would be carried in a specially designed bay in the bomber's belly, suspended from a complex trapeze system that could lower them into the airstream for launch and raise them back into the aircraft for recovery. The launch procedure would be harrowing. As the 1211-J approached enemy territory, the bomb bay doors would open and the trapeze system would lower the first Goblin into the 150-mile-per-hour slipstream beneath the bomber. The Goblin pilot would start his engine, signal ready, and then release from the trapeze to drop away from the mothership. The entire process would take less than 30 seconds, but it would require split-second timing and nerves of steel. Recovery would be even more dangerous. The Goblin would need to approach the 1211-J from behind and below, matching the bomber's speed exactly. The pilot would then need to hook onto the trapeze system while both aircraft were flying at over 150 miles per hour. A small error in speed or position could result in the Goblin smashing into the bomber's belly, potentially destroying both aircraft. Douglas engineers spent months working out the aerodynamics of the Parasite Fighter System. The wake turbulence from the massive bomber would create a chaotic environment directly beneath the aircraft. The Goblins would need to operate in this turbulent air while performing precision maneuvers. Computer modeling didn't exist in 1947, so engineers had to rely on wind tunnel tests and mathematical calculations to predict how the system would work. The Goblin fighters themselves were marvels of miniaturization. With a length of just 14 feet and a height of 8 feet, they were smaller than many of today's automobiles. Yet they packed a powerful Westinghouse J-34 turbojet engine that could propel them to speeds over 600 miles per hour. Each Goblin carried 4 50-caliber machine guns and had enough fuel for about 30 minutes of combat flying. The tactical advantages of the Parasite Fighter System were significant. Traditional bomber escorts were limited by fuel capacity. They could accompany bombers partway to the target, but they couldn't make the entire round trip. This left bombers vulnerable during the most dangerous parts of their missions. The 1211-J's Goblins could be launched specifically when and where they were needed most. But the system also created new vulnerabilities. The launch and recovery procedures would leave the bomber exposed and unable to take evasive action. If enemy fighters attacked during these critical moments, the results could be catastrophic. The Goblin pilots would also be operating at the absolute limits of their aircraft's capabilities with no margin for error. Douglas conducted extensive testing of the Parasite fighter concept using a modified B-29 bomber and actual XF-85 Goblins. The tests revealed both the promise and the peril of the system. When everything worked perfectly, the launches and recoveries were spectacular demonstrations of precision flying. But when things went wrong, they went very wrong very quickly. During one test flight in August 1948, Goblin pilot Harry Crosby attempted a routine recovery when his aircraft's hook mechanism malfunctioned. Unable to connect with the trapeze, Crosby found himself trapped beneath the bomber with rapidly diminishing fuel. The B-29 couldn't land with the Goblin attached, and the Goblin couldn't fly to an airport on its remaining fuel. Crosby was forced to bail out over the Nevada desert, becoming the first pilot to eject from a Parasite fighter. What do you think about this incredible flying aircraft carrier concept? Was it brilliant innovation or dangerous overcomplication? The answer would ultimately depend on whether Douglas could solve the technical challenges and whether the Air Force still wanted the 1211-J by the time it was ready. As 1948 progressed, the Parasite fighter tests continued, but new developments in aviation technology were beginning to make the entire concept seem outdated before it could be fully realized. The age of the jet bomber was dawning, and with it, the Douglas 1211-J's days were numbered. At the heart of the Douglas 1211-J was its primary mission, delivering nuclear weapons. But in 1947, nuclear weapons were very different from the relatively compact warheads we think of today. The bombs that the 1211-J was designed to carry were massive, primitive devices that presented their own unique engineering challenges. The Mark IV nuclear bomb, which was the standard U.S. nuclear weapon in the late 1940s, weighed over 10,000 pounds and measured nearly 11 feet in length. It was a Fat Man-type implosion device with a yield of approximately 21 kilotons. But by the time the 1211-J was being designed, American weapons scientists were already working on much more powerful thermonuclear weapons. The 1211-J was specifically designed around the theoretical requirements for carrying a 25 megaton thermonuclear bomb. To put that in perspective, that's over 1,000 times more powerful than the bomb that destroyed Hiroshima. A single 1211-J carrying such a weapon could theoretically destroy an entire metropolitan area with a population of several million people. The bomb bay of the 1211-J was enormous, measuring over 40 feet in length and 12 feet in width. This wasn't just to accommodate the size of nuclear weapons, but also to provide the complex handling equipment necessary to manage these incredibly dangerous devices. Nuclear weapons of the era required constant monitoring and adjustment during flight. Temperature changes, vibration, and altitude variations could all affect the weapon's delicate mechanisms. Douglas engineers had to design specialized environmental control systems for the bomb bay. Nuclear weapons contained conventional explosives that were sensitive to temperature and shock. The plutonium cores required precise temperature control to prevent premature detonation or, conversely, failure to detonate when intended. The bomb bay needed its own heating and cooling systems, shock absorbers, and monitoring equipment. The delivery system itself was a marvel of precision engineering. The 1211-J would need to approach its target at exactly the right altitude, speed, and heading for accurate bomb delivery. At 40,000 feet and traveling at 300 miles per hour, the bomber would need to release its weapon several miles before reaching the target to account for the bomb's ballistic trajectory. But accuracy wasn't just about hitting the target. Nuclear weapons of this era had relatively small blast radii compared to their later counterparts. A miss of even a few hundred yards could mean the difference between destroying a target and merely damaging it. The 1211-J's bombing system used a combination of radar, optical sights, and primitive analog computers to calculate the precise release point. The Norden bomb sight, famous for its use in World War II, was completely inadequate for nuclear weapons delivery. Douglas engineers developed an entirely new bombing system that could account for wind speed, aircraft velocity, target movement, and even the curvature of the Earth over long-range bombing runs. This system required its own dedicated crew member, a bombardier navigator who would spend years training on the complex equipment. Safety was another critical concern. The 1211-J would be carrying the most destructive weapon ever created by humanity. A single accident could not only destroy the aircraft and its crew, but potentially cause a nuclear detonation over friendly territory. Douglas engineers had to design multiple redundant safety systems to prevent accidental detonation, while still ensuring that the weapon would function when intended. The aircraft carried special shielding to protect the crew from radiation exposure during long flights with nuclear weapons aboard. Lead-lined compartments separated the crew areas from the bomb bay, and the aircraft's pressurization system was designed to prevent radioactive contamination from entering the crew compartment in case of a weapon malfunction. Perhaps most chilling was the 1211-J's capability for multiple weapon delivery. The massive bomb bay could theoretically carry several smaller nuclear weapons, allowing a single aircraft to destroy multiple targets on a single mission. This capability was seen as essential for penetrating heavily defended Soviet airspace, where the bomber might only get one chance to complete its mission. The psychological impact of the 1211-J was as important as its technical capabilities. The mere existence of such an aircraft would serve as a powerful deterrent to potential enemies. The knowledge that the United States possessed bombers capable of delivering 25 megaton weapons to any target on Earth would fundamentally alter the strategic balance of power. But as 1948 progressed, new developments in nuclear weapons technology were beginning to change the requirements for strategic bombers. Weapons were becoming smaller and more powerful, reducing the need for such a massive delivery platform. At the same time, new threats were emerging that would challenge the fundamental assumptions behind the 1211-J's design. The question facing Douglas and the Air Force was whether the 1211-J's nuclear delivery capabilities would still be relevant by the time the aircraft could be put into service. The answer would depend on factors far beyond the control of even the most brilliant engineers. The Douglas 1211-J wasn't just an aircraft design challenge, it was an infrastructure revolution waiting to happen. The sheer size and weight of this proposed bomber would have required the United States to completely rebuild its aviation infrastructure from the ground up. No existing airport could handle an aircraft of this magnitude. Consider the runways alone. The 1211-J, with its maximum takeoff weight of 450,000 pounds, would exert ground pressure that would literally crush existing concrete runways. The aircraft's 32-wheel landing gear system was designed to distribute this weight, but even so, each wheel would be pressing down with over 14,000 pounds of force. Most airport runways of the era were designed for aircraft weighing less than 100,000 pounds. The Air Force commissioned a study in 1948 to determine what it would cost to modify existing air bases to accommodate the 1211-J. The results were staggering. Every runway would need to be completely rebuilt with reinforced concrete at least 18 inches thick. The taxiways would need similar reinforcement. Even the aircraft parking areas would require specialized construction to prevent the massive bomber from sinking into the ground. But runways were just the beginning. The 1211-J's 230-foot wingspan meant that existing hangars were completely inadequate. The aircraft was too wide to fit through standard hangar doors and too tall to fit under standard hangar roofs. New hangars would need to be constructed with clear spans of over 300 feet and heights of at least 80 feet. These would be among the largest enclosed structures ever built. Maintenance presented its own unique challenges. The 1211-J's engines were mounted nearly 30 feet off the ground. Servicing them would require specialized platforms and equipment that didn't exist. The aircraft's electrical systems, with over 50 miles of wiring, would need diagnostic equipment that hadn't been invented yet. Even simple tasks like changing tires would require heavy machinery capable of lifting sections of the aircraft weighing tens of thousands of pounds. Fuel systems were another nightmare. The 1211-J would carry nearly 30,000 gallons of aviation fuel, more than most gas stations held in their entire underground storage systems. Refueling the aircraft would take hours using conventional fuel trucks. Air Force bases would need to install high-capacity fuel systems with pumping rates measured in thousands of gallons per minute. The logistics of operating the 1211-J were equally daunting. Each aircraft would require a ground crew of over 100 people for routine operations. This included not just mechanics and fuel handlers, but specialized technicians for the nuclear weapon systems, the Parasite Fighter recovery equipment, and the complex navigation and communication systems. Training this many specialists for each aircraft would take years and cost millions of dollars. Security was another major concern. The 1211-J would be carrying nuclear weapons and highly classified technology. Air Force bases operating these aircraft would need to be transformed into virtual fortresses with multiple layers of security, specialized storage facilities for nuclear weapons, and round-the-clock protection against sabotage or espionage. The Air Force estimated that it would need at least 12 operational 1211-J aircraft to maintain an effective strategic deterrent. This would require modifying at least 6 major air bases at a cost of over $50 million per base. In 1948 dollars, that represented an infrastructure investment of over $3 billion in today's money, and that was before buying a single aircraft. Transportation of components presented its own challenges. The 1211-J was too large to be built in a single facility and then flown to operational bases. Major components would need to be manufactured separately and then assembled at the operational bases themselves. This would require each base to have its own aircraft assembly facility, complete with specialized tooling and trained assembly workers. Even the aircraft's routine operations would strain existing infrastructure. The sound of 4 6,000 horsepower turboprop engines would be audible for miles. Communities near Air Force bases would need to be prepared for noise levels that would make normal conversation impossible when the aircraft were operating. Environmental impact studies didn't exist in 1948, but the 1211-J would have required them. The international implications were equally complex. The 1211-J's 5,000-mile range meant it could reach targets anywhere in the Soviet Union from bases in the continental United States. But for maximum flexibility, the Air Force wanted to base some aircraft overseas. This would require negotiating agreements with allied nations to build and operate the specialized facilities needed to support the aircraft. What do you think about these massive infrastructure requirements? Was the United States prepared to make such an enormous investment in a single weapon system? The answer would depend not just on the aircraft's capabilities, but on whether those capabilities would still be needed by the time the infrastructure could be built. As 1949 began, it was becoming clear that the infrastructure challenges facing the 1211-J were almost as daunting as the technical challenges. But even as Douglas engineers continued to refine their designs, events were unfolding that would ultimately make the entire project obsolete. By early 1949, the Douglas 1211-J project was facing challenges that went far beyond engineering and infrastructure. The entire strategic landscape that had given birth to the project was changing rapidly. and not in ways that favored massive propeller-driven bombers. The first blow came from an unexpected source: the Soviet Union's own technological progress. On August 29, 1949, the Soviet Union successfully detonated its first nuclear weapon, a plutonium implosion device similar to the Fat Man bomb dropped on Nagasaki. The American nuclear monopoly was over, and with it, much of the strategic rationale for the 1211-J. The Soviet nuclear test changed everything. American military planners had assumed they would have years to develop and deploy the 1211-J before facing a nuclear-armed opponent. Now, they were looking at a world where both superpowers possessed nuclear weapons, and the emphasis shifted from delivering a knockout blow to surviving a nuclear exchange. Even more damaging to the 1211-J's prospects was the rapid advancement of jet engine technology. In October 1947, just months after Douglas had begun serious work on the 1211-J, Chuck Yeager broke the sound barrier in the Bell X-1. This demonstrated that jet-powered aircraft could achieve speeds that propeller-driven aircraft could never match. The implications were profound. The 1211-J's maximum speed of around 350 miles per hour would make it vulnerable to the new generation of jet fighters that both the United States and Soviet Union were developing. The MiG-15, which first flew in December 1947, could reach speeds of over 600 miles per hour. Even with its Parasite Fighter escorts, the 1211-J would be sitting duck against such opponents. Boeing was already working on the B-47 Stratojet, a six-engine jet bomber that could fly at over 600 miles per hour and reach altitudes above 40,000 feet. While the B-47 couldn't match the 1211-J's range or payload capacity, it was fast enough to have a reasonable chance of penetrating enemy defenses and returning home. The development of surface-to-air missiles presented another threat that the 1211-J's designers hadn't anticipated. The Soviet Union was working on radar-guided missiles that could intercept aircraft at high altitudes. The 1211-J's size would make it an ideal target for such weapons. Its slow speed would give enemy radar operators plenty of time to track and engage the aircraft. Within the Air Force itself, opinions about the 1211-J were becoming increasingly divided. Younger officers who had grown up with jet aircraft saw the massive propeller-driven bomber as a relic of the past. They argued that the future belonged to fast, high-flying jet bombers that could penetrate enemy defenses through speed and altitude rather than defensive armament. The costs were also becoming prohibitive. Douglas's latest estimates suggested that each 1211-J would cost over $20 million to build, not including the massive infrastructure investments required to operate them. For the same money, the Air Force could buy dozens of jet fighters or several B-47 bombers. General Curtis LeMay, who headed the Strategic Air Command, was initially a supporter of the 1211-J project. LeMay believed in the value of massive retaliation and saw the giant bomber as the ultimate expression of American air power. But even LeMay began to have doubts as jet technology advanced and costs mounted. The final blow came in 1950 with the outbreak of the Korean War. The conflict demonstrated the importance of tactical air power and highlighted the limitations of strategic bombing against a determined enemy. The Air Force found itself desperately short of fighters and tactical bombers, while the 1211-J project consumed resources that could have been used to build aircraft that were immediately needed. In September 1950, the Air Force quietly canceled the Douglas 1211-J project. The official reason given was changing strategic requirements, but everyone involved knew the real reason. The aircraft was simply too big, too slow, and too expensive for the rapidly evolving world of nuclear warfare. Arthur Raymond and his team at Douglas were devastated. They had spent 4 years developing what they believed would be the ultimate strategic bomber, only to see it canceled just as they were solving the final technical challenges. The Parasite Fighter System was working, the structural problems had been resolved, and the nuclear delivery systems were nearly perfected. But perhaps the most tragic aspect of the cancellation was that it marked the end of an era. The 1211-J was the last serious attempt to build a propeller-driven strategic bomber. Future bombers would be jets, and they would be designed around entirely different principles of speed and stealth rather than size and defensive firepower. What do you think? Could the Douglas 1211-J have changed the course of the Cold War if it had been completed? Or was it always destined to be obsolete before it could fly? The answer lies in understanding not just what the aircraft could have done, but what its legacy means for aviation history. The death of the 1211-J marked more than just the end of a single aircraft project. It represented the end of an entire philosophy of strategic bombing that had dominated military thinking since World War II. The age of the flying fortress was over, and the age of the missile was about to begin. The Douglas 1211-J never flew, but its influence on aviation history extends far beyond what might have been. The technologies developed for this massive bomber found their way into countless other aircraft, and the lessons learned from its cancellation helped shape military aviation strategy for decades to come. Many of the structural innovations developed for the 1211-J were later applied to civilian aircraft. The advanced wing design techniques, the high-strength aluminum alloys, and the complex internal bracing systems all influenced the development of large passenger jets in the 1950s and 60s. The Boeing 707 and Douglas DC-8 both incorporated structural concepts that were first explored for the 1211-J, the Parasite Fighter System, while never successfully implemented on the 1211-J, continued to fascinate military planners. The concept was revived several times during the Cold War, most notably with the XF-85 Goblin program, and later with studies for launching fighters from B-36 Peacemaker bombers. While none of these programs achieved operational status, they demonstrated the enduring appeal of the flying aircraft carrier concept. Perhaps more importantly, the 1211-J project helped establish many of the engineering and project management techniques that would become standard in the aerospace industry. The complex coordination required between multiple contractors, the integration of advanced systems, and the management of enormous technical challenges all provided valuable lessons for future aircraft programs. The cancellation of the 1211-J also marked a fundamental shift in military thinking about strategic deterrence. The project had been based on the assumption that nuclear war could be won through overwhelming force delivered by massive bombers. Its cancellation reflected a growing understanding that nuclear war was more likely to be deterred through the threat of mutual destruction rather than won through superior delivery systems. This shift in thinking paved the way for the development of intercontinental ballistic missiles, which could deliver nuclear weapons faster and more reliably than any bomber. The Atlas, Titan, and Minuteman missile programs all benefited from resources that might otherwise have been devoted to projects like the 1211-J. The human cost of the project's cancellation was significant. Hundreds of engineers, technicians, and support personnel had devoted years of their careers to the 1211-J. Many of them went on to work on other aircraft programs, carrying with them the knowledge and experience gained from pushing the boundaries of what was possible in aviation. Arthur Raymond, the chief engineer of the project, later reflected that the 1211-J represented both the pinnacle and the end of a particular approach to aircraft design. "We were trying to solve tomorrow's problems with yesterday's solutions," he said in a 1975 interview. The aircraft was magnificent in concept, but it belonged to an era that was already ending when we began designing it. The 1211-J also highlighted the importance of timing and technological development. Even the most brilliant engineering solutions can become obsolete if they take too long to develop or if they're based on assumptions about future requirements that prove incorrect. The rapid pace of technological change during the early Cold War meant that aircraft projects had to be completed quickly or risk being overtaken by newer technologies. In many ways, the 1211-J was a victim of its own ambition. The aircraft was so advanced, so complex, and so large that it required more time to develop than the strategic situation allowed. By the time Douglas had solved the technical challenges, the world had moved on to different solutions for the same problems. The project also demonstrated the limitations of extrapolating from past experience. The 1211-J was designed based on lessons learned from World War II, when large formations of heavily armed bombers had successfully penetrated enemy airspace through defensive firepower and fighter escorts. But the advent of jet fighters, surface-to-air missiles, and nuclear weapons had fundamentally changed the nature of air warfare. Today, the Douglas 1211-J is remembered primarily by aviation historians and enthusiasts. Occasional references appear in documentaries about Cold War aviation, and detailed plans and specifications are preserved in various archives. But for most people, it remains an unknown chapter in the history of military aviation. Yet the 1211-J's legacy continues in unexpected ways. Modern military aircraft, like the B-52 Stratofortress and the C-5 Galaxy, incorporate many of the same design principles that Douglas engineers developed for their giant bomber. The concept of aerial refueling, which became standard for strategic bombers, was partly developed as an alternative to the 1211-J's extreme range requirements. The project also serves as a reminder of the incredible ambition and optimism of the early Cold War era. Engineers and military planners were willing to attempt projects that pushed the absolute limits of technology and resources. While many of these projects failed, they also drove innovation and technological advancement at an unprecedented pace. What lessons can we draw from the Douglas 1211-J today? Perhaps the most important is that technological capability alone is not enough to ensure success. The most advanced engineering solutions are worthless if they don't address real-world requirements or if they take too long to develop. The 1211-J was a masterpiece of engineering that was ultimately defeated by the march of time and changing strategic realities. The story of the Douglas 1211-J is ultimately a story about the dreams and limitations of human ambition. It represents both the incredible things we can accomplish when we push the boundaries of what's possible and the humbling reality that even our most ambitious projects can be overtaken by forces beyond our control. As we face new challenges in aviation and aerospace today, from hypersonic flight to space exploration, the lessons of the 1211-J remain relevant. The importance of realistic requirements, the need for rapid development cycles, and the danger of designing for yesterday's problems while tomorrow's solutions are already emerging. So what do you think? Was the Douglas 1211-J a magnificent failure or a necessary step in the evolution of military aviation? Could its engineers have anticipated the rapid changes that would make their creation obsolete? And what does its story tell us about the nature of technological progress itself? I'd love to hear your thoughts in the comments below. And if you enjoyed this deep dive into one of aviation history's most ambitious failures, make sure to subscribe to Never Built for more stories of the incredible machines that never were. Until next time, keep dreaming big, but remember that sometimes the most important lesson is knowing when to let go of yesterday's dreams to embrace tomorrow's possibilities.